Okay, get this. What if we could fight cancer not with super expensive gold and high-tech lasers, but with, like, common tin and a flashlight? It sounds kind of crazy, right? But today, we're diving into a breakthrough that does exactly that. It's turning one of our biggest medical challenges completely on its head with something, well, shockingly simple.
So I'm just going to put a number out there, 92%. Just let that sink in for a second. In the fight against cancer, what on earth could a number that high possibly mean? Well, that's the percentage of skin cancer cells destroyed in a lab in just 30 minutes. Yeah, you heard that right. This isn't some far-off prediction. It's a real result from a brand new study that could completely change the game for cancer therapy. All right, so let's get into it. Section 1, a shocking cancer breakthrough. We're talking about how researchers are using really simple materials to get these incredible results. A joint team from the University of Texas at Austin and the University of Porto, they've come up with something that is just, it's brutally effective, but at the same time, it's so simple, it's almost hard to believe. So the whole idea behind this, and this was just published in the top-tier journal ACS Nano, is to take a common, everyday metal, tin, and pair it with a super low-cost light source. And what's the goal? Well, it's to create this kind of targeted heat weapon that can seek and destroy tumors with absolute pinpoint accuracy. Okay, now for Section 2, the expensive gold standard. We've got to understand the old way of fighting cancer with light to really get why this new thing is such a big deal. To see just how revolutionary this new tin method is, you have to look at what we're doing right now, the current gold standard. And yeah, the name is a bit of a giveaway. It works for sure, but it is expensive, it's complicated, and honestly, most people just can't get access to it. This existing treatment is called photothermal therapy, or PTT for short. And the concept itself is pretty brilliant. You basically introduce these tiny little particles into a tumor, you shine a light on them, and they heat up, essentially cooking the cancer cells from the inside out. Sounds great, right? But the big problem has always been the materials you have to use. And here's where it gets wild. The gold standard literally uses gold nanoparticles, and you need these super powerful, crazy expensive lasers to make it work. So naturally, the whole thing is stuck in specialized hospitals and costs a fortune. Now this new breakthrough, it just swaps out the gold for simple tin nanoflakes, and it replaces that $1 million laser with a cheap LED. We're talking a dramatic drop in cost. But it's more than that. This could actually move cancer treatment from the hospital right into your home. Which brings us to Section 3, the tin and LED secret. How do these simple materials work so darn well? I mean, how can something so cheap actually perform better? Well, the secret isn't just that they're using tin. It's all about how they engineered it on a microscopic level. What they created are called snow-ox nanoflakes. Basically, using this really clever electrochemical process, they took regular tin compounds and transformed them into these flakes that are atomically thin. We're talking just a few atoms thick. It's this incredibly thin structure that's the key to their superpower. And oh boy, is it a superpower. Let's talk about something called photothermal conversion efficiency. Basically, how good are these things at turning light into heat? Well, these new tin nanoflakes have a staggering efficiency of 93%. That means 93% of all the light energy they soak up gets turned directly into tumor-killing heat. Now, to put that in perspective, the old gold nanoparticles, they top out at maybe 30 or 40%. This is a massive leap forward. And the actual process is just beautifully simple. Here are the 4 steps to targeting cancer. First, you get the nanoflakes to the tumor site. Second, you just switch on a simple near-infrared LED light. Third, those little flakes absorb the light and they heat up fast, right to a very specific temperature, around 42 to 45 degrees Celsius. And finally, that focused heat just destroys the cancer cells. But, and this is the big question, what about all the healthy cells nearby? Okay, this is probably the most elegant part of the whole thing. Here's why healthy cells are unharmed. Their robust blood flow acts like a cooling system, efficiently dissipating the heat that cancer cells cannot. See, cancer tumors, they have these really messy, chaotic blood vessels, so they're terrible at getting rid of heat. Healthy tissue, on the other hand, has this amazing circulatory system that's like a built-in radiator, constantly cooling things down. So this therapy is just so smart. It exploits that one biological weakness. It heats the area just enough to kill the vulnerable cancer cells, while the healthy tissue just cools itself off, completely unharmed. So that's the theory. Section 4 is all about the stunning lab results. And let me tell you, the data shows remarkable effectiveness and safety. The results from the lab are, well, they're nothing short of incredible. So check out these lab results after just 30 minutes of LED exposure. The team tested this on 3 different kinds of cells. The results were amazing. For skin cancer cells, they destroyed it 92%. It even showed a lot of promise for deeper, tougher tumors, wiping out 50% of colon cancer cells. But honestly, the most important number here might be that last one. Basically, 0% of healthy skin cells were harmed. Incredible selectivity. I mean, just look at this chart. You see this massive destruction rate for skin cancer, a really solid one for colon cancer, and then for the healthy cells, it's just a flat line at 0. Nothing. That level of precision, that selectivity, that is the absolute holy grail of cancer treatment. So the takeaway here is crystal clear. This method is not only powerful against cancer, it's also incredibly gentle on all the healthy tissue around it. That is what this is all about, a treatment with that dual benefit, powerful on the bad stuff, gentle on the good stuff. That is the very definition of precision medicine. Okay, so these lab results are just fantastic. But that brings us to the next big step, right? Section 5, from lab to patient. How do we get this amazing idea out of a petri dish and into a real person? What's next on the road to a real-world cure? Now, it's really important to be clear here. This research is currently at the proof of concept stage. What that means is these amazing results came from experiments with cells in a lab, not in a person yet. The next steps are going to be animal trials and then eventually human clinical trials. And that whole process, well, it can take many years. And there are definitely some big hurdles to overcome. 3 main ones, really. First, biocompatibility. Scientists have to make absolutely sure these 10 nanoflakes are safe in the human body for the long run. Second, light penetration. They need to figure out how to get that LED light to tumors that are deep inside the body, maybe using something like fiber optics. And third, delivery efficiency. They have to master how to get these nanoflakes only to the tumor and nowhere else. But when you hear the vision for this technology, it's just so inspiring. The future could be a wearable patch. I want you to just imagine this. After someone has surgery to remove a tumor, they could just apply a simple patch. This patch would have the nanoflakes, and by just turning on a light every now and then, they could zap any tiny cancer cells that might have been left behind, stopping the cancer from ever coming back. And the ultimate vision is even bigger than that, at-home treatment. Because the parts, we're talking tin and LEDs, are so cheap and so simple, this could literally democratize cancer care. It could take effective, non-invasive treatment out of the fancy, high-tech hospitals and make it accessible to everyone, everywhere. People in low-income countries, people in remote areas all over the world. So that leaves us with this incredible question. Could a simple patch and a tiny light change how we fight cancer forever? Look, it's still early days, for sure, but the science is solid, and the potential is just immense. A future where we could treat one of our biggest medical challenges with something as simple as a patch and a light? That's not science fiction anymore. It is now a real, tangible possibility.